Section 13.6, Directional Derivatives and Gradients. So we're going to start here with directional derivatives. I'm going to give you the definition way of doing it, which is not great. Then we're going to have a better way of doing it, and then a more convenient way of expressing that. So a directional derivative is going to take the concept of a partial derivative, which we know partial derivatives, remember, represent the rate of change of z in the x and y directions, so the slopes of two particular tangent lines. We're going to extend that concept so I can get the rate of change in any direction. So we extend the concept of partial derivatives to directional derivative. Partial derivatives, as I said, gives us instantaneous rate of change of the function in directions parallel to the coordinate axes. Directional derivatives allow us to compute the rate of change in any direction. If we wish to compute the instantaneous rate of change of some function with respect to distance from a point, x naught, y naught, in some direction, well, there are infinitely many directions from that point in which we could move. We need a convenient method for describing a specific direction from x naught, y naught. One way to do this is to use a unit vector. This is going to be big here. You have to use unit vectors for directional derivatives. That has an initial point at x naught, y naught, and points in the desired direction. So if I think about this, if I'm moving from x naught, y naught in some direction u, then I'm actually talking about the points along a line. That line can be expressed parametrically as x equals x naught, y naught plus su1, and y equals y naught plus su2, where these are the components again of my unit vector. Since u is a unit vector, s is the arc length parameter that has a reference point of x naught, y naught, and as s increases, we are moving along this line L in the direction of u. On the line L, the variable z, which is equal to f of x naught plus su1, y naught plus su2, substituting in these parameterizations, is a function of parameter s. The value of the derivative dz ds at s equals 0 then will give us the instantaneous rate of change of f of xy with respect to the distance from x naught, y naught in the direction of u. Has to be s equals 0, then I'm actually measuring the derivative at this point. But the rest of it will take care of. This takes care of being in the proper direction. So the first way we have of doing this, the definition of a directional derivative. If I have a function of x and y and I have some unit vector, the directional derivative of f in the direction of u is denoted, this is our symbol for the directional derivative, it is d ds of f of x naught plus su1, y naught plus su2 evaluated at s equals 0. So when I do this, I'm going to need to figure out what this is and then take its derivative. Geometrically, this can be interpreted as the slope of the surface in the direction of u at the point x naught, y naught. So, let's use this example. F of xy equals xy. We want to find and interpret du, which is f of 1, 2 for the unit vector given here. So again, my directional derivative of f at 1, 2 is d ds of, and I'm going to evaluate this function at 1, my initial x, plus root 3 over 2 s, 2 plus 1/2 s at s equals 0. So in order to do this, I actually need to know what this is. So f of 1 plus root 3 over 2 s, 2 plus 1/2 s. Well, that means I'm going to multiply these two things because my function was sy. So if we do this, we will have 2 plus, I would have 1/2 s plus the square root of 3s. So 1/2 plus the square root of 3s. And here I would have the square root of 3 over 4 s squared. Okay. So, what is my derivative? My derivative then appears to be 1/2 plus the square root of 3 plus, I've multiplied with the 2, and I get the square root of 3 over 2 s. Now I'm evaluating this at s equals 0, so what I will get is 1/2 plus the square root of 3. Square root of 3 is approximately 1.73, so this is about 2.23. So that's my directional derivative. Either answer would be acceptable, of course. So what does that mean? Well, it means that if I were to move a small distance from this point, 1, 2, in the direction of this unit vector, what I would see is that f of xy would increase by about 2.23 times whatever distance I moved. So some small distance, if I were to move 0.03 units away, then I would have a change in f of approximately whatever 0.03 times 2.23 is. So 0.06-ish. So like I said, this is the definition of a directional derivative. It is not the best way to compute a directional derivative. So we have a theorem. If I have a function which is differentiable at x naught, y naught, I can compute the directional derivative in terms of partial derivatives. Namely, the directional derivative at x naught, y naught is the partial derivative with respect to x at x naught, y naught times u1, the x component of my unit vector, plus the partial derivative with respect to y at x naught, y naught times u2, the y component from my unit vector. So I want to use this theorem to confirm the results in example 1. So in example 1, my function was f of xy equals x times y, and my unit vector was root 3 over 2, 1/2. And I know I'm looking to get the same answer of 1/2 plus the square root of 3. Well, my partial derivatives are y and x. So my directional derivative, start off by writing it generally. I know I'll have the partial derivative with respect to x times root 3 over 2 plus x times 1/2, again using my partial derivatives and those components of my unit vector. If I put in my y, the point again was 1, 2 for this problem, I will have 2 times the square root of 3 over 2 plus 1 times 1/2, which is indeed the square root of 3 plus 1/2, or 1/2 plus the square root of 3. So I can see that it is the same as what I computed in the previous example. But this is, as you can probably guess, a much simpler way of computing the directional derivative. So we'll use this method. We want to find the directional derivative of f of xy, given here, at the point 3, -2, in the direction of 1 minus j. So, the big thing here, what we have to remember with directional derivatives, we must use unit vectors. So this vector right here is 1, -1. I need to normalize this. This has a magnitude of the square root of 2. So my unit vector will be 1 over the square root of 2, -1 over the square root of 2. All right, what are my partial derivatives? I'll have 4x plus y and I will also have x minus 2y be my partial derivatives. So I have my unit vector, I have my point, I have my partial derivatives, I'm good to go. My directional derivative at 3, negative 2, I'll write it generally first, is 4x plus y times 1 over the square root of 2 plus x minus 2y times negative 1 over the square root of 2. Okay. So if I put in 3, negative 2, this will be 12 minus 2, or 10. This would be 3 plus 4, or 7. So what I would have is 3 over the square root of 2. So any small change from 3, negative 2 in the direction of 1, negative 1, or rather the unit vector 1 over the square root of 2, negative 1 over the square root of 2, is going to change the value of f by about 3 over the square root of 2 times whatever distance I have moved. Let's do some more examples. Directional derivative of f of xy equals e to the negative xy. I have here my vector is negative 1 square root of 3. So my unit vector then, if I add up these, the magnitude of this vector will be the square root of 1 plus 3, so square root of 4, 2. My partial derivatives are negative y e to the negative xy and negative x e to the negative xy. Have to remember to turn that into a unit vector. Can't stress that enough. So, my directional derivative well, if I put in 1, negative 1 here, this would be positive 1 times e to the, let's see, I'd have negative 1 times negative 1, so that would also be 1. Over here, I would have negative 1 times e to the first. Be careful with those signs, because that's tricky enough to trip even a multivariable calculus student up for this problem. So what do I have here? I have minus e over 2 and minus, this would be e square root 3 over 2, which I can leave like this, or I can rewrite in a slightly more compact version as negative e over 2 times 1 plus the square root of 3. Let's do an example in 3 dimensions. So here, this vector is 1, negative 2, 2. Its magnitude is the square root of 1 plus 4 plus 4. That's 9, so this is 3. So my unit vector needs to be 1/3, negative 2/3, 2/3. Partial derivatives I'll need with respect to x, which is 3x squared y. I'll need with respect to y, which is x cubed minus 2yz squared. And I'll need with respect to z, which is negative 2y squared z. So for my directional derivative, what I will need to do, I'm I'm going at the point negative 2, 1, 3. I'll have 3x squared y times 1/3 plus x cubed minus 2yz squared times negative 2/3 plus negative 2 y squared z times positive 2/3. So if I evaluate all of that, the 3 and 1/3, of course, cancel each other out. So I will have 4 times 1. Here I would have, what is that? That would be negative 8 minus 2 times 1 times 9, so minus 18. Negative 2/3. Down here I will have negative 2 times 1 times 3, so negative 6 times 2/3, which is going to give me 4 plus, this is negative 26 times negative 2/3, so plus 52/3 minus 4. In other words, my directional derivative is 52/3. So it's mainly about getting the general idea of how we do this and then just being careful. All right, that's the concept of the directional derivative. We're going to now talk about the concept of gradient. Gradient will give us a more convenient way to write this directional derivative as well. So, the directional derivative can be expressed as a dot product. And I can do this as the dot product of one vector whose components are the partial derivatives of f and the unit vector. This vector right here is called the gradient. If I have a function f of xy, the gradient of f is defined by, I use this symbol right here, this is an upside down triangle. Notice it's a vector, there's a vector symbol on top of that, which is the partial derivative with respect to x in the I direction and the partial derivative with respect to y in the j direction. If I had a function of x, y, and z, I then add on a z, a component in the k direction, which is the partial derivative with respect to z. So that means we can more conveniently write a directional derivative as the dot product of the gradient with the unit vector. More convenient way of writing it. For example, using the formula above, our solution to example 5 would take the form, these were the numbers we got, these were 4, negative 26, and negative 6, and we are dotting that with 1/3, negative 2/3, and 2/3. And this would give us our solution of 52/3. So this is a more convenient way of thinking of it, and once you understand it, you can actually clean up your work a little bit. So that's nice. The formula in the definition above can be interpreted to mean that the slope of the surface, z equals f of xy, at the point x0, y0, in the direction of u, is the dot product of the gradient with u. So if we look here, I have u, I have my gradient. Their dot product, which is, of course, their magnitudes times the cosine of the angle between them, is going to give me this slope right here. Some properties of the gradient. The gradient is not merely a notational device to simplify the formula for directional derivative. For instance, let's rewrite the formula for the gradient using the definition of a dot product. So, we know that this means I would have the magnitude of the gradient at x0, y0 times the magnitude of u times the cosine of theta But use a unit vector so I can drop that and say the gradient of f at x naught y naught times cos theta, where theta is the angle between the gradient and u. That tells us that the maximum value of the directional derivative occurs when theta equals 0. That is, when the gradient is in the same direction as the unit vector. Or rather, it would make more sense probably to say when my unit vector is in the same direction as the gradient. Okay? So I maximize my directional derivative by going in the direction of the gradient. By that token, I would minimize if I were to go in the opposite direction. Geometrically, at xy, the surface z equals f of xy has its maximum slope in the direction of the gradient of f, and the value of the maximum slope is given by the magnitude of the gradient. Similarly, since the minimum value occurs when theta equals pi, thereby I would have cosine of pi as -1, when the gradient of f is in the opposite direction of u, I will have my minimum value for my directional derivative, which will be the negative of the magnitude of the gradient. And I should note here, I've dropped writing x naught, y naught because this hasn't thrown an x naught, y naught out. But of course, the magnitude of the gradient will very much depend on what point I'm looking at. So geometrically, this again means that the minimum slope is in the direction opposite the gradient. And the value of the minimum slope is given by the negative of the gradient. In other words, if I'm right here, if I go in this direction, I have the most rapid increase. But if I go in the opposite direction, I'm instead getting the most rapid decrease. In the case where the gradient is equal to the 0 vector, it follows that the directional derivative must be 0 in all directions at that point. This typically occurs where the surface has a relative minimum, maximum, or a saddle point. And this will come up again when we talk about finding minima and maxima for functions of multiple variables. All right, let's take a look. In the following examples, we want to find the gradient of f, we want to evaluate that gradient at p, and we want to find the rate of change of f at the point p in the direction of the vector u. Now it's worth noting, well, no, it's not worth noting, it's essential to note that both of these vectors are unit vectors. If they're not unit vectors, you have to normalize them. You have to make them unit vectors. So I find my partial derivatives. I would have 5y squared minus 12x squared y and my partial derivative with respect to y will be 10xy minus 4x cubed. So the gradient is simply this vector, 5y minus 12x squared y, 10xy minus 4x cubed. The gradient at the point 1, 2 then would be, if we go through and evaluate this, this will be 10 minus 24, so negative 4. Wait a minute, I said that wrong. Oh, 5y squared. 20 minus 24. There we go. 10xy. If I evaluate this, I will have 10 times 1 times 2, so that's 20, minus 4 times 1, so 20 minus 4 is 16. So then, my directional derivative will be the dot product of negative 4, 16 with 5/13, 12/13, which is negative 20 plus 16 times 12 is what? $192. So my directional derivative is 172/13 for that unit vector at the point 1, 2. Example 7. I want to find the gradient in general and at this point, and then the directional derivative for this unit vector. So, my gradient the derivative with respect to x, I have a constant y times the natural log of x. So my partial derivative is y over x. My partial with respect to y will just be the natural log of x. At 1, negative 3, y over x is negative 3, and I'll have the natural log of 1. The natural log of 1 is, of course, 0. So then, my directional derivative at 1, negative 3 is negative 3, 0 dotted with negative 4/5, 3/5, which is 12/5. So we can see that this is, again, it's useful, but it's also very convenient for computing directional derivatives. It cleans up our work significantly. All right, another property that we should know. The gradients will be normal to level curves. So if we assume that f of xy has continuous first-order partial derivatives, which for our purposes generally that's what's going to happen, and that the gradient is not the 0 vector, then the gradient of f at x naught, y naught is normal to the level curves of f through x naught, y naught. So I want to show that the level curves of f of xy equals x squared plus y squared are circles, and verify that the gradient is normal to the level curves. So I can think about this, and I have k is equal to x squared plus y squared. And it's not hard to see that those are circles. If k is negative, I will have no solutions. If k is 0, I will have the origin. If k is 1, I'll have a circle of radius 1. For a circle of radius 2, when k is 2. No, I have a circle of radius square root of 2, excuse me. So that would be like here. And I'd keep going like this. I'd get to a circle of radius 2 when k is 4. I'm not drawing these real well. It might make more sense to just draw k equals 1, k equals 4. If I go to 3, I would of course have k equals 9. Not drawing these circles particularly well, forgive me. Yeah, that big miss. Sorry. So we want to show that the gradient is normal to the level curves. Well, what is the gradient? The gradient of f is 2x, 2y. So, the gradient of f at 3, 4 is 6, 8. The gradient of f at negative 4, negative 3 is negative 8, negative 6. Notice the gradient does not need to be a unit vector. I stress in the unit vector for when we're doing directional derivatives, but gradient is just whatever. So if we do this, if we draw this right here, at the point 3, 4, I would need I don't have that on here, do I? These would be on the I go out to 5, that would be on k equals 25. But 6, 8 is going to point out like this. Negative 8, negative 6 will point out like this. And it will in fact be normal. That's just kind of a general drawing. If you want to make an argument that it is normal, what you would need to do is find the slope of a tangent line here. Okay. When examining a contour map, we instinctively regard the distance between adjacent contours to be measured in a normal direction. If the contours correspond to equally spaced values of f, then the closer together the contours appear to be, the more rapidly the values of f will be changing. It follows from this section's theorems that this rate of change is given by the magnitude of the gradient. Thus, the closer together the contours appear to be, the greater the length of the gradient. That was kind of subtle. But again, what this is talking about is if I look down here at this contour map, the gradient measures the rate of change at a particular instant. Well, if I'm, say, out here going towards 6, this is a slow rate of change because I have a good deal of space to cover before I get up to that next level. But when I'm going from 6 to 10, for example, I'm going up over a shorter distance, so this appears to be a steeper rise. This will be steeper still, steeper, and steeper. So for this contour plot, we want to sketch the directions of the gradients at points P, Q, and R, and we want to think about at which of these 3 points does the gradient have maximum length or minimum length. And again, maximum or minimum among these 3 points. So, what we discussed, gradients are normal to level curves, and they will point in the direction of increase. So from 2, I will point towards the higher level curve, where k is 6. So normal to this, I might have something kind of short like that. Here I have a steeper increase, so I will see a longer gradient vector for q. R, this is even closer, so I will see a still longer gradient vector, which again, these are all normal to my different level curves. You don't need to mark that, but I'm doing that for emphasis. Maximum length will be at R, where the next highest level curve is closest. Minimum length will be at Q, excuse me, not Q, P, said that wrong, where the next highest level curve is furthest away. Application. There are numerous applications in which the motion of an object must be controlled so that it moves towards a heat source. And you're thinking about like medical diagnostics, locating heat sources generated by tumors, heat-seeking missiles used in the military. These are some fancy applications for gradients. As an illustration, we want to consider the temperature at any point on a flat metal plate. In this case, the gradient of T of xy gives the direction of the greatest change of temperature at the point xy. So if you were to see this image, the idea is I would follow the gradient to go to the greatest increase in temperature if you were really cold, and I would go in the opposite direction if you were really hot. Example 10 right here, the temperature in degrees Celsius on the surface of a metal plate is given by T of xy equals 20 minus 4x squared minus y squared, where x and y are measured in centimeters. In what direction from 2, negative 3 does the temperature increase most rapidly, and what is the rate of increase? Well, we know the most rapid increase is going to be in the direction of the gradient of f. So my gradient is negative 8x, negative 2y. The gradient at 2, negative 3 is negative 16, 6. So this is the answer to our first question. This is the direction of most rapid increase of temperature. What is the rate of increase? Well, the rate of increase will be the magnitude of that gradient, because we know we're going to take the dot product with a unit vector, and if we want to maximize it, we need the cosine of 0. So again, the maximum increase is the magnitude of that gradient. Which there are a variety of ways to compute this, especially if you want to actually simplify this. That is the square root of 292, which 292 is 4 times 73. So that's 2 square root 73 if you do want to reduce it. Or you could just approximate it. This is about 17.088. Don't need to reduce it. I'm just showing off. Hopefully that makes sense. If you have any questions, let me know.